Now we'll transition away from trapezoid to something called Simpson's rule. As we make this transition, let's remember the two-subdivision trapezoidal rule to the integral. It involved function evaluations at the two endpoints as well as a function evaluation at the midpoint. Our notation is I, T2, trapezoid, two subdivisions, the integral of f from a to b. For any function f, the Simpson approximation to the integral is defined as follows. The notation is for Simpson, f ab. And it's b minus a over 6 times fa plus 4f at the midpoint plus fb. So notice that both approximations require three function evaluations at both endpoints and at the midpoint. However, in making an approximation to the integral, the formulas weight the points differently. Well, what's special about Simpson's rule? Let's look over its accuracy and error bounds. It turns out that if f is any cubic polynomial, then the integral of f from a to b is, which is exactly the Simpson formula. So, Simpson's formula is exact for cubics. The integral of a cubic can be accomplished with three function evaluations. Remember how the trapezoid formula works, and for two subdivisions, it's not exact even for quadratic functions. Also, as we noted on the previous slide, both require three function evaluations. How about error bounds for this Simpson formula? The error bounds for trapezoid involve the second derivative of f. The error bounds for Simpson involve the fourth derivative of f. Suppose that the fourth derivative of f, I'll mark that f4, is bounded by some constant m4 in the interval a to b. In other words, the absolute value of the fourth derivative of f is less than m4 for all x in the interval a to b. Then, the error between the Simpson approximation and the actual integral is bounded by m4 times b minus a to the fifth power over 180. Like the trapezoid error bound, this can be proven with calculus, but we won't bother doing that here. We'll use it, though, as we derive an error bound for a composite Simpson rule. In the meantime, though, let's prove the top theorem that states that Simpson's formula is exact for all cubic polynomials. We'll start with the cubic polynomial x cubed. The integral of x cubed from a to b is nothing more than a quarter b to the fourth minus a to the fourth by the fundamental theorem of calculus doing the antiderivative. We can expand b to the fourth minus a to the fourth as this expansion. Just multiply that out, check for yourself. Now let's break up the term b cubed into 2/3 b cubed and 1/3 b cubed, as well as the term a cubed into 1/3 a cubed and 2/3 a cubed. The inner four terms, 1/3 b cubed plus b squared a plus ba squared plus 1/3 a cubed, is actually just b plus a cubed divided by 3 by the binomial theorem, or simply multiply it out and verify. Now let's put a factor of 2 in the b plus a. So divide b plus a before taking a cube by 2, and then pull out the 2 cubed, which is a factor of 8 in the numerator. So there I've just introduced a factor of 8 and a factor of 1/8 in the two terms. Doing a little arithmetic can simplify this. 1/4 of 2/3 is a sixth, and 1/4 of 8/3 is 4. Notice that we have b cubed, b plus a over 2 cubed, a cubed. This is nothing more than f of b plus 4f of b plus a over 2 plus f of a. And finally, you notice that this is exactly what we called Simpson's rule. Now let's move to the next step and verify the same identity for a quadratic function. Integral of x squared is 1/3 b cubed minus a cubed. Follow the same steps as on the previous slide, but actually it's quite a bit simpler. And again, you will arrive at Simpson's formula, also works for quadratics. Step 3, do this for linear. Integral of x dx is 1/2 b squared minus a squared. Again, follow the same steps and convince yourself that this is also Simpson's formula. Finally, the last step, do it for a constant function, the constant function 1. Integral of 1 is b minus a a few simple steps, almost nothing to do here, and it is again Simpson's formula. And now we can put these pieces together to prove that Simpson's rule is always exact for any cubic function. How will we do that? Well, we remember that integration is linear and Simpson's rule itself is linear. Namely, for integration, the integral of a scalar times a function is that scalar times the integral of the function, and the integral of the sum of two functions is just the sum of the integrals. Linearity for Simpson's rule means that the Simpson formula applied to alpha times f over the interval ab is just alpha times the Simpson formula applied to f over the interval ab. Remember what Simpson's formula is. It's f evaluated at three particular points, added together and scaled by a number. So if f changes by a factor, clearly that quantity changes by the same factor. And that's all we mean here. Likewise, if we apply Simpson's formula to the sum of two functions, again remember, Simpson's formula evaluates a function at 3 points, adds them together with different weightings, and scales that. So applying this to the sum of two functions is the same as applying it to the two functions individually and then adding them back up. Since we've established Simpson's rule is correct for a pure cubic, a pure quadratic, a pure linear, and a pure constant, it must be true by these ideas for any linear combination of those. And a linear combination of x cubed, x squared, x, and 1 is what we call a general cubic function. So we have proven the exactness of Simpson's rule for cubics.